Okay, welcome back. Where are we? Number 13. Um, Set up the integral to find the volume of the solid. Do not evaluate. Right, so the region z equals 6 minus x squared minus y squared, and z equals 0. So z equals 0 is the xy plane. And then this thing, what is that? So you could do that sort of chapter 11 analysis where you look in all the three different planes and kind of piece it together. It's going to be a parabolic ellipsoid, but in case you didn't know that, you kind of go, plane by plane, right? So in the xy plane, when z is equal to 0, you're going to get 0 equals 6 minus x squared minus y squared, and then solve for, so you get x squared plus y squared is 6. And then that's just a circle with radius square root 6. Okay, so you get some sort of circle there. And then you go to the yz plane. So that's when x equals 0. So you get z equals 6 minus y squared. And in particular, then, that's just a parabola flipped upside down and shifted up 6 places. 1, 2, 3, 4, 5, 6. Right? So it's going to look like that. Then finally, in your xz plane, letting y equal 0, we get that z equals 6 minus x squared. Okay, so again, you have one of these parabolas, and at the end of the day, it's looks like that, right? Right. Right, and we need to find the volume underneath this thing in the XYZ, over top of the XY plane. So normally it would go down infinitely, but we just want to know the volume of this object here, this kind of upside down bowl. All right, so what we're doing is setting up a triple integral to accomplish this feat. And when you're just finding volume, all you need is a 1 inside here for your function. And then you choose your orientation. And usually I think the standard orientation is going from z equals 0 to the surface. And then you go y equals curve to y equals curve, and then x equals point to x equals point. Okay, so I'm going to go dz, dy, dx. And that would be considered kind of my standard orientation. So starting out, z equals 0 to z equals this surface. Z equals 0 is the xy plane to this surface right here, this cup thing. And it's right here. These are actually the bounds on the limits on the first integral. So z equals 0 to z equals 6 minus x squared minus y squared. You can almost guess your way through a lot of these problems. Anyways, for the xy plane, then, the region that I'm integrating over, I kind of already have it sort of drawn out over here. So I need to integrate the entire thing. So I go from y equals this curve to y equals this curve, right? So I'm going to need some square roots. So if I solve this thing for y, it'll end up being y equals plus or minus square root of 6 minus x squared, right? So I'd have minus square root 6 minus x squared to positive square root 6 minus x squared. And then the Riemann man is running from negative root 6 to positive root 6, okay, in the standard orientation. Right? All right, so negative root 6 to positive root 6. And that would be the answer. Okay, let's look at another one. So some of the ones in the book are kind of pretty intensive, especially with regards to rewriting orders. They want you to rewrite in all 6 orders. I probably won't have you go that far. Maybe just rewrite it into 1 or 2 orders. Anyways, let's look at our integral. So I have from 0 to 12 minus 3x minus 6y all over 4. So that's going in, so there's f of x, y, dx, dz, dy. Okay, and then I have 0 to 12 minus 3x minus 6y all over 4. Okay, I'm right. And then 0 to 4 minus x all over 2. And then 0 to 4. Okay. And I need to kind of reorder it in the order of x, z, y. So sorry, this is the part that's wrong. Originally, it's given in z, y, and then x. Okay, sorry about that. And I want to go to x, z, y. Okay. So I want to go x equals some surface to some other surface, and then z equals some curve to some curve, and then y equals point to point. Probably the surface to surface part is the hardest if you don't have a picture. I think on the one on the test I give you a picture, but on this one it's a pretty simple thing. It's just a plane, so I expected the students to be able to do that in class. So to be able to draw that plane, well, what is this? It's z equals that thing. So z equals 12 minus 3x minus 6y all over 4. And if you think about it, you need the x, y, and z axis intercepts to draw it. So when x and z are 0, you're getting the y-intercept. You'd have 0 equals 12 minus 6y over 4. Multiply both sides by 4, you get 6y is 12, so y is 2. When x and y are 0, you get z equals 12 over 4. In other words, z equals 3. And then when, what do we need now? The y and the z are 0, you get 0 equals 12 minus 3x over 4. In other words, 12 minus 3x is 0, so 3x is 12, so x is 4. Okay, so I can draw that, right? I can get a picture of what that looks like in the first octant, at least. So I'm going from y equals 2 will be out here. Z equals 3, 1, 2, 3 is right here. X equals 4, 1, 2, 3, 4 is right here. And then you can connect those, and that's your plane. Okay. It goes on infinitely, but at least in the first octant, that's what it looks like. So what? Well, what this thing is saying is that you're integrating from the surface z equals 0, which is the xy plane, to z equals this thing, which is that guy right here, right? So z equals 0, the xy plane, that's this kind of triangle region right here. Okay. And then I'm going from there up to this surface. It extends out everywhere. Okay. Okay, so it's like you can imagine a little dot there, and then I'm going up to this surface here. Okay. All right. So, and then in the xy plane, what am I doing? I'm going from y equals 0 to y equals 4 minus x over 2. So what is that 4 minus x over 2? Well, it's just basically this thing, right? It may not be obvious, but that's exactly what it is. Let's be 100% sure, right? So look, if you let z equals 0, you'd have 0 equals 12 minus 3x minus 6y all over 4. Okay? And then you could solve for y. So multiply both sides by 4, you get 12 minus 6y equals 3x. Do some more rearranging. Sorry, I didn't rearrange very well there. 6y equals 12 minus 3x, and then divide both sides by 6. You get 2 minus 3x over 6, which is 1 all over 2, and then a common denominator will give you 4 minus x over 2. So it is, in fact, just this intersection right here, this line in the xy plane is basically this curve here. So I'm going from y equals 0 to y equals 2 minus x over 2, so y-intercept of 2, and then down 1 over 2, and then down 1 over 2 is this curve, which I'm saying is basically this line right here. And then I'm going from 0 to 4 on the x-axis, so my Riemann is going in this direction. Okay. All right. So it's basically this triangular sort of solid that I'm finding the volume of with that triple integral. I'm integrating over it, but that's the thing. Okay. All right. So I need to change the order to begin with dx. So to begin with dx, you're going from now, instead of the xy plane, you're going to from the plane that excludes x. So the zy plane. So this is x, this is y, this is z. The zy plane is going to be this rectangle back here. And I'm running out of colors. I needed like a red or something. Okay, so it's actually going to be this plane back here where you're starting. So that's x equals 0. And then you want to go out to this plane here that we had before, right? This plane again. So I want to start on this back plane and then shoot forward until I hit this plane that's going through the first octant. All right, so the integral then, I need to get this thing in terms of, instead of x and y, I need it in terms of y's and z's, right? So I'm going from x equals 0 to x equals this plane, which I need to now rewrite in terms of y and z. So I have z equals 12 minus 3x minus 6y all over 4. And I just need to kind of invert it, right? So I'm going to move the 4 over 4z is 12 minus 3x minus 6y. Move the 6y over, or better yet, move the 3x over and the 4z over. So 3x equals 12 minus 6y minus 4z. And then divide both sides by 3. So I get x equals 12 minus 6y minus 4z all over 3. Okay, so x equals 0 to x equals this thing. And that thing again is going to be 12 minus 6y minus 4z all over 3. And so that's surface to surface. And then we go curve to curve. And that's just going to be kind of this thing sort of situation, but now in the YZ plane. So it's really this red rectangle that you're zooming in on. So for the red the red triangle. So for the red triangle, I'm going from curve to curve. Okay, so in this case, I need to work with this, but with x equaling 0. So in that case, z equals 12 minus 6y all over 4. And that would be this curve right here. Okay? So it's going from z equals 0, which is this curve, and this is my orientation, to z equals 12 minus 6y over 4. So 12 minus 6y all over 4. And then the Riemann is running from 0 to this point right here, which is where z equals 0. So I'm going from 0 to this point. I need to let z equal 0. So if z is 0, I'll get, well, you'll get this point right here, which we already know is 2. Okay, so that will be 0 to 2. And then, whatever my function is, f of x, y, and then the order dx, dz, dy. Okay. All right. So let's see what we got next. Convert the integral to cylindrical coordinates, do not evaluate. All right, so this is number 15. And where are we? Black pen here. Maybe this will work. Sure. Okay, so they're giving us this triple integral. Maybe write it. It seems like if I write it, oh great, that pen died. Kind of put it like this, and it becomes a little easier to read. In case you have to write really long things in the integrals. So in this case, I have x squared plus y squared to 4, and I have x dz, dy, dx, and then I'm going from negative square root of 4 minus x squared to square root of 4 minus x squared, and then I'm going from negative 2 to 2 on the outer integral. Okay, so in that case, I want to go to cylindrical. It's basically just polar coordinates, right? I'm not going to worry about spherical coordinates on the test. I'll skip over that junk. Seems like if you do astronomy, I think then you're going to have to deal with some sort of spherical system. I doubt they even use spherical coordinates though. So. But it'll be more like spherical coordinates, I think. Seems like 5 years ago I looked into it, and it seemed like that. I don't remember. Anyways, everything is changed into r, dr, r, theta, and z. Okay, and you could kind of pull it off, at least on the inner part, just by letting this be in terms of r's and thetas, right? So x squared plus y squared is just r squared, and then to 4, and then x is rewritten as r cosine theta, and then you're going to have a r dz dr d theta, so another r on top of that would give you r squared cosine theta, then what did I say, dz dr d theta, right? All right. For the outer parts of the integral, then you need to really look at what this thing is telling you. So what is the picture, in other words? This negative thing is the lower semicircle of centered at the origin with the radius 2, right? So it's going to be this curve, and then this curve, y equals that, is the top circle, the upper semicircle right here. Okay, so I'm going from here to here, curve the curve, and then the Riemann man is running from negative 2 to 2 on the x-axis. So negative 2 to 2. So it turns out we're integrating the entire over the entire circle. The polar equation is r equals 2. So remember, the running man is now running in the circular orientation, going from the origin out to here. So the origin 0 out to 2. And then I'm rotating all the way around from 0 to 2 pi. Okay. All right. So that's just the setup. Let's look at the next guy, so number 16. Now we have to evaluate this integral that's kind of already been rewritten. 0 to e to the negative x squared. Another pen bites the dust. 0 to e to the negative x squared. Hopefully you can read that. Maybe a different color is in. Okay. And then stepping out one further, we have 0 to 3. And then one further even is 0 to the pi over 2. And the integrand is r dz dr d theta. Okay, so I need to integrate first with respect to z. Okay, so I didn't need that extra integral. So it will just be z times r, and I have to evaluate dr d theta from 0 to whatever, e to the negative x squared. Okay. So I'm plugging that stuff in for z. So it's the double integral of e to the negative, and and that should be an r, not an x squared. I apologize. R squared there. R squared there. Okay, so plugging in this for z will give me e to the negative r squared times r. And then minus, when I plug 0 in there, that'll just be 0. So we need not write that. And then we have dr d theta. And then we got to do a u sub. So u is negative r squared. Du is negative 2r dr. So dr is negative du all over 2r. And then we could rewrite this integral as r times e to the u times negative du all over 2r d theta. And then you can factor out the r's will cancel, right? So the r's are gone. But then you can factor out a negative 1/2 exponent, or sorry, constant. And then you have the double integral of e to the u du d theta. And the integral of e to the u is just e to the u, so you got negative 1/2 integral of e to the u evaluated d theta. Okay. And then we have negative 1/2 integral of e to the now, what are the bounds on that guy? 0 to 3. But I still need the back sub, my u, so I can't literally write that just yet. So I have e to the negative r squared. I'm evaluating from 0 to 3. Okay, so d theta. So this would be negative 1/2 integral e to the negative 9 minus e to the 0 d theta. All of that is just a constant, which I can factor out of the integral. So I have negative 1/2 times e to the negative 9 minus 1. And then the integral of just 1 d theta will be theta. And I have to evaluate that from 0 to pi over 2. So that's just going to give me negative pi over 4 times e to the negative 9 minus 1, and then minus 0, but you know. Okay. Oh, one more. So this is number 17 now, and it's a Jacobian, full-on Jacobian. So this is worth a little more because it's longer, so it's worth 10 points. There'll definitely be one like this on the test. So use change of variables to find the value in solid region lying below the surface. F of x y equals x plus y times e to the x minus y. This should be f of x y. Sorry, it just looks crazy. And the region I'm integrating over is I guess it's a rotated square with vertices 4, 0, 6, 2, 4, 4, and then 2, 2. Okay. And your first sort of task is to find equations for these, for the lines, for the edges of the square. 0, 4, 1, 2, 3, 4, 2, 2, 1, 2, 1, 2, and then 4, 5, 6, 2. Okay, so you want to find these lines in terms of x's and y's, and then you want to pick your u's and v's, so your integral is kind of like a box integral. So it goes from like 0 to 1 and then 0 to 1. Okay, and then do your substitutions with your Jacobian, and hopefully things work out real nice like. Okay, but usually it's a little bit time consuming to do all of the pre-work to the integral. So let's just take a look at that. In particular, then I'm gonna sort of work with this line and this line first. Okay, so I need equations for those lines, and maybe it's even good to kind of note what these points are, so I don't screw it up too much. Right. Okay. So in particular, then 2, 2 to 4, 4. The slope is going to be 4 minus 2 is 2. All over 4 minus 2 is 2, so it's a 1. And then I have y minus 2 equals 1 times x minus 2. And you want to get all the x's and y's on one side and the number on the other. And that's the variable side is what's gonna be your u or your v. Okay, I'll let it be my u. It doesn't matter. Okay, so I'm going to move, I guess, the y over and then move the 2 over. Okay, so it doesn't really matter as long as I want to be consistent with my notes, though, so I don't make any mistakes. So what I did in my notes was, I got to find my notes. What did you do? X minus y. Okay, so if you have x minus y here, so that means I added 2 to both sides, and I'd have 0 for 1. Then I need this other guy here, so that's from 4, 0, and 6, 2. It has the same slope. Those lines are parallel. I can just tell if you're not sure, you can always go through, y2 minus y1, x2 minus x1. Okay. Then I'm going to get my equation. So y minus 0 equals 1 times x minus 4. And again, I'm going to put x and y on one side. So move the y over, you get x minus y. Add 4 to both sides, you get 4. Okay, so this stuff I'm going to let be u, I believe. Let that be u? Yeah. Okay. And what it's telling me is that the limit on my integral is going to go from 0, which is from here, to 4. And that makes everything so much easier, right? Okay, now I need to get my v, and for my v, I'm going to use these 2 lines. Okay, so I'm going from 2, 2 to 4, 0. And its slope, 0 minus 2 is negative 2, 4 minus 2 is 2, so it's negative 1. And then it's y minus 0 equals negative 1 times x minus 4. So I get y equals negative x plus 4. And then I'm going to move the x over and I get x plus y equals 4. Okay? So I'm going to let v be the x plus y in this case. So I'm going to note that as well. So right now u is equal to x minus y. And then I'm going to let my v equal x plus y. Okay. Okay, I need the other line. So this guy up here, that's from the 4, 4 and the 6, 2. And so I got a slope is 2 minus 4 is negative 2, all over 6 minus 4 is positive 2, which is negative 1. And then you go 1 minus, I guess I'll use the 4, 4. So y minus 4 is negative 1 times x minus 4. So I got y minus 4 is negative x plus 4. Add the x over, x plus y is equal to, what, 8? Okay. So that tells me sort of the limit on my v part of the integral. V is going to end up going from 4 to 8. Okay, I'm going to need a Jacobian. In order to get the Jacobian, I need to get the partial derivatives and the way the book is doing it. There's other ways, but we just want to be consistent with the book, so I'm not throwing 50 million different ways at you. You got enough to worry about. So I'm going to go and solve for x and y, and then I can do the partials for my Jacobian. Okay, so now I'm solving for x and y in terms of u's and v's. So first I'm going to solve for x here. X will equal u plus y, and then you do a substitution in the here. Okay, so v will equal u plus y, and then you solve for y. Okay, so 2 y's will end up being v minus u, and then y will equal v minus u all over 2. Then you take that job and you smush it back into here. Okay, so you'll have x equals u plus y, which is now v minus u all over 2. Common denominator of 2 means x is 2u plus v minus u, which is u plus v all over 2. And now I can get my Jacobian. So my Jacobian is the magnitude of the determinant. And in my case, The partial with respect to u of this, of x, is 1/2. And the partial of y with respect to v is also 1/2. Minus the partial now of this with respect to v, which is 1/2, times the partial of this with respect to u, which is negative 1/2, which will end up being 1/4 plus 1/4, which is 2/4, which is 1/2. Okay. So I got all my material. Now I need to just dump it into my integral. You could do any order you want because it's just over a box and the new setting. So I'm going to go from 4 to 8. Now let's go 0 to 4 and then 4 to 8. Well, what did I do on my integral? Yeah, that's what I did. Okay. And then I'm doing a substitution for x and y. Okay. So x is now u plus v all over 2. And it's going in for this, in case you're wondering. So I'm letting x now equal this. And then y must equal this thing, because that's kind of what I'm after. I'm after the double integral of r of x plus y e to the x minus y dA. That's my goal, right? And it's kind of an annoyance when you have a box like this. So what we did was all this work to just turn it into a regular box in the UV plane. Okay, so it's that plus y, and y is v minus u all over 2 times e to the x minus y, which is u plus v all over 2 minus now v minus u all over 2. And then I've chosen u, so du dv. Okay. Okay. Clean this stuff up. Usually they clean up pretty nice, like so u all this the u over 2's will cancel, leaving you with 2v over 2, so you get v, and then e to the power of, okay, in this case the v over 2's will cancel, leaving you with 2u over 2, which is just u, and then you go du dv. And I almost forgot my Jacobian of 1/2. Okay, which I'll smush into my integral, but it's going to pop out because it's a constant. So I'll just put it right there. Okay, and I'm going from 0 to 4 and 4 to 8. Okay, almost there. Then I'm going to integrate first with respect to u, so I get 1/2 integral of v e to the u, and evaluate that from 0 to 4 dv. That'll be 1/2 integral of v e to the 4 minus e to the 0, which is 1 dv. And then you want to factor this material out in front. So you'll get e to the 4 minus 1 all over 2 times the integral of v dv. Okay, and then the integral of v is v squared over 2, so I'll have another factor of 1/2, so it would be e to the 4th minus 1 over 4 times v squared, evaluated from 4 to 8. Okay, so I have e to the 4 minus 1 all over 2 times v squared, which is 64, and then minus 16, right? 64 minus 16, which is 24, or something like that. Did I screw something up? Oh, I lost my 4 right here. That screws it up. And then 64 minus 16. What do we get? 8, and then 4, and then divided by this 4 would just be 12. So it would be 12 times e to the 4th minus 1. That's it. All right. I'll put up the test next week, so you'll have to download it and then upload it. I'll probably put it up. I don't know when I'm going to put it up. Probably on Wednesday night, and then I'll probably give you till Tuesday night to back upload it, or to send it to my email. I can't figure out how to upload on the Blackboard if there's multiple files involved. So you'll probably just send it to my email, then I'll grade it and send it back to you. All right. All right. So hope everything's going well with you. Hope you're staying healthy. Just hang in there. Semester is going to be over before you know it. And good luck. Okay. All right. Bye-bye.